welcome back once again to trigonometry. Every time I say trigonometry, I think about my puppy that we had. We actually, two math nerds. Actually had a dog named Trigonometry. God rest her soul. Lost her due to bone cancer, but I think about her every time I say that. Alright, so let us wrap up our discussion on graphing trig functions by looking at cosecant and then secant. These are the last two of the reciprocal functions. Last podcast talked about the tangent and its reciprocal cotangent. So now we're going to look at cosecant, which is reciprocal of sine, and the secant, which is reciprocal of cosine. So we'll go through each one and talk about the basics of graphing them. Okay, so let's talk about the cosecant first. Okay, the cosecant of x, again, is reciprocal of sine, so it's the same thing as saying 1 over sine x. And graphing it, you basically are graphing 1 over sine x. So let's say you have xy table here, x, and let's compare sine x values versus cosecant x values. And then once we do the table, we'll plot them and also see what they look like in graph form. Okay, let's start with 0. We can start with anywhere, but let's just start with 0. It's a good place to start. When you do the sine of 0, you get 0. But then if you do 1 over that for the cosecant, remember this is 1 over sine x reciprocal, you're going to get 1 over 0, which is undefined. Now when we did cotangent and we had something undefined, it was a vertical asymptote. And that's exactly the same thing that's going to happen here. Everywhere that your sine of x graph would cross the x-axis, the cosecant x graph is going to have a vertical asymptote. Okay? Let's continue and see some more things about the behavior. Pi over 6, the sine of pi over 6 is 1/2. The cosecant of pi over 6 is the reciprocal of 1/2, which is 2. For pi over 3, sine of pi over 3 is square root of 3 over 2. The reciprocal of that is 2 square roots of 3 over 3. For pi over 2, the sine is 1. Reciprocal of that is 1. For 2 pi over 3, sine is square root of 3 over 2. Reciprocal of that is 2 square roots of 3 over 3. For 5 pi over 6, the sine is 1/2. The reciprocal for that is 2. Okay, so far, then we get to pi. Sine is 0. Cosecant is going to be undefined. So far, the numerical pattern for sine, as we go from 0 to pi, sine starts down at 0, climbs up through 1/2, through square root of 3 over 2, peaks at 1, then starts climbing back down steadily through square root of 3 over 2, 1/2, back down to 0. So you've got your sine graph that's doing this so far, while the cosecant graph, on the other hand, has the undefined thing going on right here, starts out up higher, starts dipping down, hits 1, and then starts dipping back up, and then there's your vertical asymptote. Well, let's do some more values here and continue. Let's see what happens next. Right, 7 pi over 6, if you do the sine of that, you get negative 1/2. If you do the reciprocal for cosecant, you get negative 2. For 4 pi over 3, you get negative square root of 3 over 2 for the sine. For cosecant, you get negative 2 square roots of 3 over 3. When you get to 3 pi over 2, sine is negative 1, cosecant is negative 1. When you get to 5 pi over 3, sine is negative square root of 3 over 2, cosecant is negative 2 square roots of 3 over 3. So we have this relationship happening again, but now down on the negatives. 11 pi over 6, sine is negative 1/2, cosecant is negative 2. At 2 pi, sine is 0, Cosecant is undefined. Alright, so over at 2 pi, your sine graph has dipped down and then come back up. Your cosecant graph, on the other hand, has started at 7 pi over 6. It was a -2, and then it was climbing up to -1, and then climbed back down to -2, like this. And in fact, if you got finer values here between 0 and pi, if you looked at smaller values in there, you see that this curve just keeps heading up like this. And if you got finer values between pi and 2 pi, you see that this curve keeps heading down like this. But the curves never cross those vertical asymptotes. The vertical asymptotes are limits, if you will. The curve gets closer and closer to them, but never actually touches them. And this keeps going. This repeats. Cosecant has a period of 2 pi. The asymptotes occur at integral multiples of pi. The range actually goes from -infinity to -1 and includes -1, and then picks back up at +1, including +1, and goes to infinity. And just like the sine graph, cosecant is an odd function. So cosecant of -x is the same thing as negative cosecant of x. If you look at it closely, you'll see the origin symmetry. Okay, so what is your best bet for graphing these? Well, your best bet is to first graph the sine. In fact, I'm going to do that in red. Well, first let me mark this off. Let's mark this off. 1, 2. Let's put pi over 2 right here. Put pi here. 3 pi over 2 here. 2 pi here. And then let's go the other direction. Negative pi over 2. Negative pi. Negative 3 pi over 2. Negative 2 pi. You can go further, but that's as far as we're going to go for now. And let's go 2, 3, 4. Let's make that 1. 1, 2, 3, 4. Let's make that 2. It keeps going. 1, 2, 3, 4. Negative 1. 1, 2, 3, 4. Negative 2. Keeps going. Your sine graph can start at 0, go up to 1 at pi over 2, go down through pi, go down to -1 at 3 pi over 2, and come back up to 2 pi. That's your sine graph. And in this direction, we go down to -1 here, go to negative pi here, go up to 1 there, go back down to -2 pi there. It's 2 pi periodic. The wave pattern is going to continue in a very steady manner. Right? But when you're doing your cosecant, so the red is the y equals sine x. When you're doing your cosecant, y equals cosecant x, everywhere the sine was 0, you're going to have a vertical asymptote. So it is much easier to go ahead and graph the sine first. It makes it way easier for whatever interval you need to graph it, the cosecant for. Graph the sine for that interval. Then you can see wherever the sine graph crosses the x-axis, you know where your vertical asymptotes have to be. That tells you a lot there. And then you can see wherever the peaks, maximums are, you know where some points for the cosecant have to be, and then you know which way to send the curves. Okay. Alright, so there's the vertical asymptotes. At each of these, at the maximums, the cosecant has a point as well. And at the minimums, the cosecant has a point as well. And what happens with the cosecant is if you start plotting all those points, you get these curves that look like this. Okay, so so now you can see why the domain is all real numbers except integer multiples of pi, because the vertical asymptotes are negative 2 pi, negative pi, 0 pi, 2 pi. You can keep going with integer multiples like 3 pi, 4 pi, 5 pi, and you're going to see vertical asymptotes. The range, the y values, go anywhere from negative infinity up to negative 1, including negative 1, and from positive 1 up to infinity. They don't include the values in between. They don't include the values between negative 1 and 1 for the range. But there's your cosecant graph. So as long as you've plotted some key points from your sine graph, you can quickly sketch the cosecant graph. Okay, let's try another cosecant. Let's do y equals cosecant of x plus pi over 4. Well, basically it's plus pi over 4 tells us it's the cosecant graph shifted to the left, pi over 4 units. That's what this right here tells us. But you can also think about it as graph y equals sine of x plus pi over 4 first. Okay, amplitude is 1. Because a here is 1. And then you got negative 2 pi, so less than or equal to x plus pi over 4. Or I could use 0. I don't know why I did negative 2 pi. I could go to 0 here. I think as I was thinking about the interval from negative 2 pi or whatever. Let's do 0 here, just to get one of the intervals. Sorry. Less than or equal to 2 pi. Alright, if you subtract negative pi over 4 from all three parts, you end up, and then 2 pi minus pi over 4 is going to give you 7 pi over 4. You end up with that. Okay. So from negative pi over 4 to 7 pi over 4, that's where the sine's going to be situated. So it's been shifted over pi over 4. So let's see here. If we put negative pi over 4 right here, and then 2, 3, this is pi. 1, 2, 3, this is 2 pi. Let's go ahead and go to 3 pi. Alright, so the sine graph will start at negative pi over 4, go up to, so here's 1, here's negative 1. I'll go ahead and mark off a little bit more for you. Okay. So shift to negative pi over 4. So instead it's going to go up, and it's going to peak halfway between here. There's pi right there. So it's going to peak, you got 1, 2, 3, 4, 5 of these. 1, 2 is going to peak right here. Ah, my goodness, I'm trying to situate this. Hang on a second. Alright, negative pi over 4. Let me do this first. The one go around would be 2, There's, I'm trying to figure out where I labeled pi and 2 pi. See, pi is here, 2 pi is here, and it's shifted over. So it's going to end up right here. It's going to have to go up, and then it's going to go back down halfway in between. It's going to go back down. That's pi. It's so hard to draw on this thing. Be glad you're using paper and pencil or something. Alright. Goes right here. Then halfway between those, it's going to peak. And then halfway between those, it's going to go down to here. There we go. Alright, so it does that. And then at 1, 2 over, it's going to peak. 1, 2 over, it's going to go down. And at 1, 2 over, it's going to go down. It's just going to keep going like that. You'll do that in this direction too. Okay, that gives you the sine. But then to do the cosecant, start drawing your vertical asymptotes through the places where you see x-intercepts. Okay, then wherever this dips down to its lowest points, that's going to be the top point of one of these curves. And wherever this goes up to one of its highest points, that's going to be the minimum of one of these curves. But all the blue that I'm drawing, that's your y equals cosecant of x plus pi over 4. And you could keep going. You know, it's 2 pi periodic, so every 2 pi it repeats. But the entire graph got shifted left pi over 4 units. So there it is. Alright, so that was cosecant. Now secant is very similar, y equals secant x. Because remember, secant's the same thing as 1 over cosine. So you, and then since sine and cosine are sinusoidal, you know, you can take sine and shift it and get cosine. Secant is basically cosecant shifted. That's really all it is. Same kinds of principles apply. You graph cosine, wherever you see x-intercepts, there you're going to have your vertical asymptotes, and whatever you have your peaks and valleys, you're going to see where to put the maximum and minimum type points for your secant. So like if x is 0, we know that cosine of 0 is 1. Secant of 0 is going to be also 1, because reciprocal of 1 is 1. If you got pi over 3, cosine of pi over 3 is 1/2. Reciprocal of that is 2 for secant. So while cosine is a smaller number, secant is a larger number. At pi over 2, cosine 0, secant's going to be undefined, because 1 over 0 is undefined. At 2 pi over 3, you got negative, cosine's negative 1/2, secant's going to be negative 2. At pi, cosine's negative 1, secant's going to be negative 1. At 4 pi over 3, cosine's negative 1/2, secant is negative 2. At 3 pi over 2, cosine is 0, secant's going to be undefined. At 5 pi over 3, cosine is 1/2, secant is 2. And at 2 pi, they both turn out to be 1. Like that. But to graph it, basically you can graph the cosine function first. Alright, so cosine, let's see, let's mark it off. 1, 2, -1, -2. Mark it off here. Cosine starts up here at 1, and then it dips down. Goes down at pi, it hits -1, and then it dips back up. And at 2 pi it hits 1 again. So it does, it's just like the sine curve, except it's shifted over a little bit. Alright. So my eyes keep messing up where I'm seeing things. I'm sorry. Pi over 2 is right here. That's what I get for being blind in one eye. I have a hard time sometimes seeing things. Alright, so here we go, and then it's going to go down to -pi. Alright, so you get your cosine graph on there. And then, once your cosine graph's on there, you can take for your secant and say, well, every time I see it going through the x-axis, I know that I have a vertical asymptote there. Yep. At the peaks, you know that you're going to have a minimum point for your secant, and at the valleys, you know you're going to have a maximum type, a local maximum for your secant. Say local, just right. There is no actual maximum or minimum for secant because these shoot way up to positive infinity and these shoot way down to negative infinity. But locally, just within that little region, you have little local maximums and minimums. You'll talk about local maximums and minimums in calculus. Okay, but that's how you can get your secant graph. Graph the cosine first, and then go through and start putting in your secant stuff. Okay, so looking at that, it's still, you have a period of 2 pi. Your domain is all your reals except odd multiples of pi over 2, because you have, like, you leave out negative pi over 2, negative 3 pi over 2, positive pi over 2, positive 3 pi over 2, positive 5 pi over 2, odd multiples of those. So pi over 2 times 1 times 3 times 5 times 7, or times -1, -3, so forth. Those are going to be your vertical asymptotes. Notice your range goes from negative infinity to 1, 1 to infinity, and this is an even function. So just like cosine, this is even, or just like, yeah. So secant of negative x equals secant x, This one has y-axis symmetry. Your domain, all reals except odd multiples of pi over 2. At those places you have your vertical asymptotes. And your range, just like cosecant, is negative infinity to negative 1, union 1 to infinity. And you can see that in the graph. Okay, let's graph one more of these secants just to make sure we're good. Then maybe we'll stick one in the calculator and look at it. Let's graph y equals 2 secant 2x. But to do that, let's first graph y equals 2 cosine 2x. And then use that to help us to figure out what 2 secant 2x should be. Okay, 2 cosine 2x, the amplitude is going to be 2. And then the period is 2 pi over 2, which equals pi. There's no phase shift on this one. Okay, so let's go ahead and plot that first. This time I'm going to label better because it just really helps me to see things visually when I have it all labeled. Okay, we'll go the other direction too. Alright, it's saying amplitude to period of pi. Here's 1. Here's 2. Up there's 3. Here's negative 1. Negative 2. And way down here is negative 3. Okay. So cosine, instead of starting at 1, it's going to start at 2 because the amplitude is 2. And then it's going to come down. The period is pi, so it's going to come down and go back up and end at pi. Halfway between, it'll be at its lowest point. So when we hit pi over 2, it'll be down here at negative 2. And then it's going to go through the x-axis at pi over 4 and at 3 pi over 4. Let's go a little bit further. Let's see here. Come back down to the x-axis there. And then come all the way down to negative 2 right there. And it will come back down to the x-axis here. And go all the way to negative 2 here. Go back up. But that's enough to give us an idea of what to do. So that's the 2 cosine 2x. That's the amplitude of 2. So it peaks, from the axis here, it peaks up 2 and then it drops down to negative 2. and then cosine 2x, so we figured out the period was going to be pi. So it did this nice horizontal squashing. But then for y equals 2 secant 2x, we're going to do vertical asymptotes through places where the cosine crossed the x-axis. So for each of those, you have a vertical asymptote. You could keep going for as long as they tell you. Like, just see what, sometimes they specify what interval to do this over. Other times they'll specify, like, start here and do, this many of them. So just go as far as they tell you to go, like whatever interval or whatnot. Okay, so we have a point here, and then we can draw a curve pointing up from there. And then we have a point here, we can draw a curve going down. We have a point here, we can draw a curve going up. If you want to, you can start, finding specific values and plotting them to get prettier curves. I'm just sketching quick curves. You gotta look to see too how many points they ask you to label. If they ask you to label, 3 points on the curve, then go ahead and look specifically at where 2 more points would be on this curve, or 2 more points would be on this curve. But for now, I'm just, sketching. This is adequate if you're just quickly sketching the graph. But that's basically what y equals 2 secant of 2x would look like. Let's see how this would do in the calculator, because let's compare. Let's put 2 cosine 2x in. And then let's put 2 secant 2x, but that's 2 times 1 divided by cosine 2x. And let's go ahead and make that one thicker, and then hit graph. And there you go. It doesn't draw the vertical asymptotes, but at least you know where they're supposed to be. But there's the relationship between them. But notice I did have to put in, like, the 2 out front, that's 2 times whatever you're dealing with, 2 times secant 2x. Secant 2x is 1 over cosine 2x. It's a reciprocal function. So when you're putting in secant or cosecant, you got to do 1 over whatever it is. If you're putting in cosecant, you got to do 1 over sine. Or if you're putting in secant, you got to do 1 over cosine in the calculator. But there you go. That graph looks pretty similar. It's a little nicer than mine, but you see the same pattern existing there. Okay, that's it for now on the reciprocal functions, graphing those. Thank you for joining us. We have some practical applications we need to talk about next, especially involving harmonic motion. I think that lesson's a lot of fun, so do stay tuned and join us next time for harmonic motion and practical applications.